Okay, this is lecture 6.2, Substitution and Area Between Curves. Let's start with a review of the fundamental theorem of calculus. So there are two parts to this theorem. Part 1 says if we have a function, f of x, that is continuous on a closed interval, then this new function, capital F of x, this is defined to be the area under the curve. This is like the cumulative area under the curve. This function is continuous and differentiable everywhere except possibly the endpoints. Moreover, the derivative of this cumulative area function is the function itself. So as an example of this, let's suppose that we have a function f of x, and let's say it's continuous on at least ab. Now this capital F of x function is the cumulative, keeps track of the area under the curve, and here x is our variable. So this area function is not only continuous, but it's differentiable, except possibly at the endpoints. And the reason why is because our original function might have a corner or something like that, in which case the area function is not going to be differentiable at a. Okay, so part 2 says that if f of x is a continuous function on an interval, think of f of x as like the rate of change of something, so like velocity. And big F of x is any antiderivative, then if we add up our rate of change times the actual quantity on the entire interval, then that's just equal to the original function, the antiderivative, evaluated at the endpoints. So think of this as adding up velocity times time over the entire interval. That's just equal to the difference in positions. So to motivate this, without a motivation, this is abstract and hard to understand. So to motivate this, let's consider an example of traveling by car from Clemson to Charleston. And we want to figure out how far we've traveled. So one way to do this is to plot. Suppose we keep track of our velocity as a function of time. So this up here is v of t. And so for the first hour, say we drive up to Interstate 26. It's near Spartanburg, so it takes an hour to get there. We are going 60 miles an hour. Well, I guess to get up to Spartanburg we need to go faster than 60, but don't worry about that. So for the first hour we're going 60 miles an hour. Then the next 2 hours we're going on Interstate 26, so we are going a little faster. Let's say that we are going 75 miles an hour for 2 hours. Now, of course, we don't go from 60 instantaneously up to 75. This looks like a step function, but realistically we speed up very quickly, but in a continuous fashion. And let's say that these corners are really smooth, so we take sandpaper and smooth off these corners. So this is a differentiable function. Although I guess it's not required to be differentiable. All that's required is that it's continuous. And finally, the last hour, we get near Charleston. We're north of the city, and there's traffic, as there usually is. So say we are going at 30 miles an hour for the last hour. So for 1 hour, we go at 30 miles an hour. Of course, this is continuous, so we quickly slow down, and that's our trip. So one way to figure out how far we've traveled is just divide our trip into segments. Now for the first hour, we have traveled at 60 miles an hour for 1 hour, so obviously we have traveled 60 miles. Now the second leg, we have gone 75 miles an hour for 2 hours, so we have clearly gone 150 miles. That's supposed to be a 0. Looks close enough. And then the last leg of the journey, we have gone 30 miles an hour for 1 hour, so we've gone 30 miles. So our total distance is equal to 60 plus 150 plus 30, which is equal to 240 miles. That's one way to do this. Of course, that's not what you're going to do, realistically. I mean, there's a much easier way to do this, and that's looking at your odometer. So when you arrive at Charleston, you look at your odometer, and well, I guess when you leave, you should probably check your odometer first. And at time equals 0, suppose your odometer says 10,000 miles. Now when you arrive, now that should be at 4, your odometer says 10,240. So clearly your distance is simply x of 4 minus x of 0, which is 10,240 minus 10,000, which is 240 miles. So without knowing it, you are doing the fundamental theorem of calculus. Notice that this side, adding up the rate times time for the entire interval, that's the left-hand side of the equation. Gets you 240 miles. Alternatively, you can take the antiderivative, which is position, and evaluate that at the endpoints. Take the difference, and that gets you the same answer. And that is part 2 of the fundamental theorem of calculus. So, now that we've reviewed that, let's move on to u-substitution. So we're changing gears a little bit. Okay, so I have 2 examples. The first one does not require u-substitution, and the second one does. So for the first example, notice that the antiderivative of 3x squared is x cubed. So I need to evaluate that from -1 to 1. So this is 1 cubed minus -1 cubed, which is 1 plus 1, which is equal to 2. There's our answer. Now the second one, you look at this and say, u-substitution should jump out because you look at the inside and x cubed plus 1, well, the derivative of x cubed plus 1 is 3x squared, which is sitting out here. So we let u equal x cubed plus 1, and we do this because now du dx equals 3x squared. So if we multiply dx on the other side, we get du equals 3x squared dx. And that's what we have. That's what we have right there and right there. Okay, so plugging this back in, this becomes the integral of the square root of u, I'll write that as u to the 1/2, times du. Notice that is exactly what we have. But we got to be careful with the endpoints, or I guess the limits. So x equals -1. We can't just say u equals -1. We have to figure out what u is equal to when x is equal to -1. So when x is equal to -1, u equals -1 cubed plus 1, which is equal to 0. So I'm going to put a 0 here at the left endpoint. Now when x equals +1 up here, then u equals +1 cubed plus 1 equals 2. So the upper endpoint is at 2. So now we have an integral that is easy to compute with u. So let's do that. So this integral is going to be equal to u to the 3/2 over 3/2 from 0 to 2. So this is 2/3 times u to the 3/2 from 0 to 2. So this is 2/3 times 2 to the 3/2 minus 0 to the 3/2. We can ignore that 0. And so notice we have a 2 to the 3/2 here times 2 is going to give us 2 to the 5/2. So that's going to be 2 to the 5/2 divided by 3. And there is our final answer. Okay. Next, let me summarize what we did: substitution and integration. So the theorem that we used is if g prime is continuous on a closed interval and f is continuous on the range of g, then this mess holds. Now, I'm not even going to bother reading this. I'll just let you look at it. But this is not something you should memorize. I mean, I don't have this memorized, and you shouldn't either. What you should need to know is how to use it. It's better to understand what's going on, understand the examples, and practice it. Don't memorize this. Think of it like grammatical rules in English. And if I were to ask you a question about what's the grammatical rule for what case or what tense you use, you don't know it. You know how to use it, but we've all probably had the experience of trying to explain to a non-native English speaker what the grammatical rule is, and we don't know the rule, but we know how to use it. And this is a perfect example of where you should focus on understanding the examples and being able to do it rather than actually memorizing every nitty-gritty detail of this rule. Okay, let's do one example, one more example. Let's evaluate this creature here. So to do this, I look at this, and u-substitution should jump out because you look at, there's obviously no formula for this integral, but if you look at this, the derivative of that is going to be sine, which is on top. So to do this, let's let u be equal to the bottom 2 minus cosine of t. Now, du dt equals sine of t, and that tells us that du equals sine of t dt. And notice that is exactly what we have right there. Okay, so now we need the limits. So let's see. So the limits. The lower limit, this is when t equals 0. So let's say t equals 0. So u is equal to 2 minus cosine of 0, which is 1. So that is equal to 2 minus 1 equals 1. The upper limit is when t equals pi. So t equals pi, that happens when u equals 2 minus cosine of pi, and that is 2 minus negative 1 equals, that's just 3. And if you forget about where, cosine of pi, cosine of 0, just think of the unit circle. this is 0 radians, and this here is pi. So this is theta equals 0, and this here is theta equals pi. And the cosine is just the x value, so it's positive 1 here, and it's negative 1 there. Okay, so now to do this back to our integral, we are actually integrating from 1 to 3, and let's see, where were we? So our function is, so we had 1 over u, and then this part was our du. So 1 over u du, and this is equal to the natural log of u evaluated at 1 to 3, and this is the natural log of 3 minus the natural log of 1. Forget the natural log of 1 is equal to 0, so this is the natural log of 3. So this is another example of, you know how to do u-substitution, you're substituting back in, you're checking the limits, but at no point did I have this theorem memorized, and I probably would have, if I had to write this down without notes, I would probably mess it up at some point. But all that's important is that you know how to use it. Okay, now I want to review a few shortcuts for integration. You may or may not have seen this, but I think both of these are going to be very intuitive. First of all, a function is even, f of x is even, if this condition holds, f of x equals f of negative x for all x. What this is saying in plain English is that f of x is symmetric about the y-axis. Okay, so if we have a function that's symmetric about the y-axis, it's easy to see that if f of is even, then the integral about a symmetric interval is just twice the integral from 0, or twice the one-sided interval. So as an example of this, this is just saying, let's do an example like this f of x is even because f of a, that's up here, whatever that is, this is f of a, that's equal to f of negative a. So clearly the area under the curve, just by simple symmetry, is going to be equal to double the area under the curve of the right region of this. And that's all there is to it. Now, examples of even functions, the word even comes because even polynomials are, even degree polynomials are even. So I'll say examples. So what are some examples of even functions? F of x equals 3. That's an odd number, but it's an even function. F of x equals x squared, or x squared plus 1, there's an even function. X to the 4th plus 3x squared minus 5, that's an even function. What else? Cosine of 3x minus x squared, there's an even function. If you add up two even functions, you get an even function. If you multiply an even function by a scalar, that doesn't change the symmetry. What else is there? Well, there are some others that we'll see shortly. What else? Odd functions. So an odd function, a function f of x is odd if f of x equals negative f of negative x for all x. This is just saying that f of x is symmetric about the origin or equivalently across the x and the y-axis. So let's do a picture. Well, actually, before say what the result is if f of x is an odd function, then if we integrate it about a symmetric interval, we get 0. And this is quite obvious from the picture. Let's just draw an odd function. So an odd function, it might look like, well, if it's defined like this on f of x, then that just means it's going to be like this on 0 to negative a. And so it should be clear that the area under the curve is going to be 0, because this is positive area, and that's going to cancel with the negative area. And the reason why I say symmetric about the origin is if I take any point here and I reflect it across the origin, suppose this is x, so this is f of x, then this is negative x, and this is negative f of x. Right there. So that's the type of symmetry we get. Examples of odd functions. Examples, well, f of x equals, how about x cubed minus 2x? Well, f of x equals x. F of x equals, what else? How about sine of x? That's an odd function. What else? Let's write down a few that are neither even nor odd. X squared plus x minus 3. That has both even and odd terms. So I don't know what it looks like, but it's not going to have either even nor odd symmetry. E to the x, that is not going to be even nor odd. And then there's a lot of them. What about cosine of x plus sine of 2x? That's not even nor odd. Okay, next I want to show you how to compute the area between the two curves. So let me give you a proposition. If f and g are continuous on a closed interval and f of x is greater than g of x, or at least as big, then the area of the region between the curves is just you integrate the difference of the two functions. And this should be this should be easy to see with an example. Let's suppose this is f of x, and let's suppose g of x looks like, let's make it like that, g of x. And then on this region, a and b, notice that f of x is greater than or equal to g of x on a, b. So this integral right here, now, if you want to, you can write this as the integral from a to b of f of x dx minus the integral from a to b of g of x dx. And that's really why this works, is because notice this first integral is just this area under f of x. And then this second integral, this one over here, this blue one, is just the area right here. So the area that we're looking for is the difference of the red and the blue area. And so it's just, that's why we have this formula right here. So it should be fairly self-explanatory. Okay, let's do an example. Find the area enclosed by the curves y equals root x and y equals x minus 2, and the x-axis. So the first thing we have to do is draw a picture of this. We can't do it if we can't visualize it. So root x looks, well, that's supposed to be at the origin, looks something like y equals root x, and then x minus 2 looks something like this, and then the intersection I think is going to be at 4. So the area we seek is, it's the area that is under this curve and above this piecewise curve. So we have to break this into two pieces. The first piece, let's call this A, and the second piece is going to be this region. Let me call this B. So the area is going to be A plus B. And this first integral is going to go from 0 to 2. Now it's because it's along this base of under root x and above 0, and then plus this next integral is going to go from 2 to 4. It's going to be under root x and below above x minus 2 dx. So this first integral, now remember that root x is just x to the 1/2. So this first integral is going to be x to the 3/2 over 3/2 evaluated from 0 to 2 plus, what do we have here? Well, we have x to the 3/2 over 3/2 from 2 to 4 minus x squared over 2 from 2 to 4 plus 2x from 2 to 4. Okay, so this is, let's simplify this. This is equal to 2 thirds, 2 to 3/2. We could ignore this 0, so we have plus, so let's see, now we have 4, square root of 4 is 2, 2 cubed is 8, so we have, so that's, let's be careful here, let's put the 2/3 out front, and then that's going to be 8 minus 2 to the 3/2. Notice that this term is going to cancel with that term, so we can just get rid of them, and then minus, we have 4 squared over 2 is 8, minus 2 squared over 2 is 2, and then plus 2 times 4 is 8, minus 4 times 2, 2 times 2 is 4. So let's simplify this. So this is going to be 16 thirds minus, that's going to be 6. So let's see, so this is equal to 6, and this is equal to 4. So 6 is equal to 18 thirds, and 4 is equal to 12 thirds. So this is 10 thirds, and that is our final answer. Okay, so after doing this, we look back and we say, well, we had to break this into 2 integrals, and that gave us 4 terms, and that was a little bit lengthy. And there's actually a better way to do this. Let's look back at this function. Let's look back over here and notice if we had made this a function of y instead of x. In other words, if we had reflected this across the line y equals x. So let's suppose that this is the vertical axis, this is the horizontal axis. Then we are going under this, so under this function, that means in that direction, and above that function, and we would have only needed to compute one integral. So let's do it that way. Let me first draw what we had so I can compare. So I had a function y equals root x, and we had the function y equals x minus 2, and this intersection was at 4, and this intersection was at 2. Now this is the x-axis, and this is the y-axis. So let's draw this as a function of y instead of a function of x. So if this is the y-axis and this is the x-axis, now it's easy to make a mistake here. So I'm going to switch to red for this. So this is x equals y plus 2, and this function right here is x equals y squared. So let's draw these. X equals y squared looks like that, and x equals y plus 2 looks like that. Now this intersection is at 2, and this intersection is at 4. And again, this is x equals y plus 2, and this is x equals y squared. And now we are trying to find this area. Let me call this A, area here. And so the area equals A. This is so we're integrating now from 0 to 2 under the curve y plus 2 and above the curve y squared dy. Now let me do this one in one fell swoop instead of breaking it up into 3 integrals, just to change it up. So now this is the integral of 1/2 y squared plus 2y minus 1/3 y cubed. And we are going from 0 to 2. So I can ignore the 0. Plugging in any of those terms is going to give me 0. So this is 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 cubed. So this is 2 plus 4 minus 8 thirds. So this is 2 plus 4 is 6. That is 18 thirds minus 8 thirds, and that is 10 thirds, and that is exactly what we had when we did it the other way.